Hi there, Miss Barber here. This lesson is titled Events Involving and Conditional Probabilities. You toss a fair coin 12 times. All 12 times it lands heads up. What is the probability that on the 13th toss the coin will land heads up? The coin is fair, which means that it is unbiased and the likelihood of both tails up and heads up are equal. With that said, the results of the previous tosses have no bearing on the probability outcome of the next event. Thus, the probability that this coin will land heads up on the 13th toss is still 1/2. The probability of independent events. 1. Two events are independent if the occurrence of either of them has no effect on the probability of the other. 2. If A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. We write the probability of A and B as the probability of A, the intersection symbol, B, and read the symbol that's the upside down horseshoe as and. Example, let's suppose that the probability that a region in Tornado Alley will be hit by a major tornado in a single year is 4/17. A. What is the probability that it will be hit by a major tornado for 3 consecutive years? This is actually set up like a counting principle problem. We're concerned with year 1, and the likelihood of a tornado is 4/17. The next year, year 2, the likelihood of that major tornado is still 4/17. And the third year, same likelihood, 4/17. The result is 64 divided by 4,917, or we might just say 1.3%. Part B, what is the probability that that region will not be hit by a major tornado in the next 5 years? Well, if the probability of being hit is 4/17, then the probability of not being hit would be the complement, 1 minus the probability of being hit, which would then be 1 minus 4/17, and that is equal to 13/17. Now we need 5 consecutive years of not hit. That's a counting principle problem, so we'll have 5 years, each of which has 13/17 probability of not being hit. 13/17 second year, 13/17 third year, 13/17 fourth year, and 13/17 fifth year. Multiplied through, that is 371,293 divided by 1,419,857, or we would just say about 26.15%. The probability of an event happening at least once. Let's consider you toss a fair coin 3 times. List all possible outcomes, which is also called the sample space. You could have heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, and then 3 tails. That's all the possible outcome of tossing one coin 3 times. What is the probability of getting no tails? Notice that you have 8 possible outcomes and only one event in which there are no tails. That's the 3 heads, one time. So the probability of no tails is 1/8. Notice that the remaining 7 events has at least one tail. So you can count them out and you have 1, 2, 3, 4, 5, 6, 7 events that have tails. So that probability is 7/8. We can also compute it as the probability of at least one tail is equal to 1 minus the probability of no tails. That would be 1 minus 1/8, which was the 7/8 we just counted. From this exercise, we see how to compute the probability of an event happening at least once. That is equal to, we say the probability of an event happening at least once is equal to 1 minus the probability that the event does not happen at all. Example, let's suppose that the probability that a region in Tornado Alley will be hit by a major tornado in a single year is 4/17. Find the probability that the region will be hit by a major tornado at least once in the next 5 years. We previously determined that the probability of that region not being hit by a major tornado as 26.15%, or we could express it in decimal form 0.2615. Using the formula, the probability event happens at least once is equal to 1 minus the probability not hit by tornado in the next 5 years. We can write this as 1 minus 0.2615. That difference gives us the probability whose value is 0.7385. We conclude the probability that this region is hit by a tornado in the next 5 years is 73.85%. Example, you are playing a version of Among Us with 9 players of which 3 are imposters. They are named A, B, C, D, E, F, G, H, I. You select 3 players randomly. What is the probability that you select at least one imposter? To solve this problem, we first find the probability of selecting no imposters. To do this, we use the combination counting method. For the probability of no imposter, that's going to be equal to, we've got 6 that are not imposters. Of those, we want 3. So C, 6, 3 times, and we have 3 who are imposters. We don't want any of them. So we multiply that by C sub 3, 0. That's our event space. Our sample space, we've got 9 players and we pick any 3. So that's C, that's combination of 9, choose 3. Use your calculators to compute each of these combinations. C, 6, choose 3 is 20. C of 3, choose 0 is 1. And the C, the combination of 9, choose 3 is 84. We can reduce this to 521. So the probability of getting no imposters is 521. Thus, when we compute the probability of at least one imposter, which would be 1 minus the probability of no imposter, we will have 1 minus the value we just computed, 5/21, and that difference is 1621. The probability that you select at least one imposter is 16/21, or about 76.19%. The probability of dependent events. 1. Two events are dependent if the occurrence of either of them have an effect on the probability of the other. 2. If A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. The notation would be probability of A upside down horseshoe B is equal to the probability of A times the probability of, the notation is B straight bar A. It is read B given A. 3. The probability of event B, assuming that event A has already occurred, is called the conditional probability of B given A. This probability is denoted by P open parentheses B vertical bar A close parentheses. It is read the probability of B given A and is computed as the probability of B and A divided by the probability of A, as long as the probability of A is not 0. Example: 3 students are randomly selected, 1 person at a time, from 6 freshmen, 3 sophomores, and 2 juniors. Find the probability that the first 2 students are sophomores and the third is a freshman. Since the students are selected without replacement, we use probability for dependent events. That is, we want the probability of a sophomore and a freshman in that order. We will first compute the probability of the first sophomore and then multiply it to the probability of the second being a sophomore, given that a sophomore has already been selected, and then we multiply that to the probability that the third is a freshman, given that a sophomore has been selected for the first and the second position. Before we compute the numbers, let's go ahead and make a basket and put in tickets that represent each of the students. So I will put in 6 tickets with F for the 6 freshmen, 3 tickets labeled S for the 3 sophomores, and 2 tickets labeled J for the 2 juniors. Then from this basket we see the probability of getting a sophomore on the first attempt is 3 sophomores out of 11 total possible. Now that we have selected 1 sophomore, the probability of selecting a sophomore on the second attempt, that lowers our sample space down by 1 to 10, and we have only 2 sophomores remaining. So the probability of a sophomore selected on the second selection, assuming that 1 was selected on the first, is 2/10. Now in that basket with all the tickets in it, we have 1 less sophomore. We now have 9 in the sample space. We want a freshman for the third one, and there's still 6 freshmen remaining. So the probability of selecting a freshman on the third attempt, given that a sophomore was selected on the first and a sophomore was selected on the second, is 6/9. The probability of a sophomore, then a sophomore, then a freshman is the product of these 3 probabilities, which is 36 over 990. This reduces to 2/55. Example, selected from Thinking Mathematically, textbook, page 751. The data provided in the table are based on 100,000 U.S. women ages 40 to 49 who participated in mammography screening. This table consists of 4 columns and 4 rows. The columns, the last 3 are labeled breast cancer, no breast cancer, and total. The rows, the last three are labeled positive mammogram, negative mammogram, and total. Reading across starting at positive mammogram, the inputs are 720, 6,944, and 7,664. For negative mammogram, reading horizontally, the numbers are 80, 92,256, and the last entry in the totals column is 92,336. The last row, called total, reading horizontally, is 800,000, then 99,200, and finally 100,000. Assume that these numbers are representative of all U.S. women ages 40 to 49. Find the following probabilities. A. Has a negative mammogram given that she does have cancer. We are looking for the conditional probability so that the probability of M negative given C positive. Using the formula for conditional probability, this is equal to the probability of M negative, that's negative mammogram, and positive cancer at the same time, divided by the probability of positive cancer. Using our table to compute, the intersection of a negative mammogram and breast cancer is 80 out of 100,000. For the probability of positive cancer, the cancer total is 800 out of 100,000. We simplify this complex fraction to 80 over 800, which is 10%. What does this mean? It means that if you have breast cancer, the probability that the mammogram will say otherwise is 10%. Part B, has cancer given that she has a negative mammogram. This is a conditional probability written as the probability of positive cancer given negative mammogram. The conditional probability formula, we write this as the probability of positive cancer and negative mammogram divided by the probability of negative mammogram. Let's use our table to find the values. The probability of both having breast cancer and negative mammogram, the point of intersection is 80, so it'll be 80 over 100,000. And the probability of a negative mammogram, reading horizontally across to the totals column of the negative mammogram, is 92,336, and we divide that by 100,000. Simplifying this complex fraction, we get 80 over 92,336, which is about 0.000867. That is, if you have a negative mammogram, the likelihood that you have cancer is very low. Example, you are playing a version of Among Us with 9 players and 3 are imposters. They are named A, B, C, D, E, F, G, H, I. You sequentially select 5 players randomly. Find the probability of the 5th being an imposter given that you have already selected exactly 1 imposter. Let's set this up like a counting principle problem. In this instance, we are concerned with only the 5th selection. Let's count this out. We'll make a basket and put a ticket in representing each player, so there will be 1 for each of A, B, C, D, E, F, G, H, and I. We have already selected 4 players, so we'll get rid of 1, 2, 3, and 4. Now, to compute the probability of the 5th position, Notice that there are only 5 players remaining, and of the 3 imposters, 1 is already picked. That means only 2 remain. So the probability of the 5th being an imposter, given that you have already selected exactly 1 imposter, is 2/5.